And this is our official start of data structures for today. We have, oops, there we go. Today we're going to talk a little bit more about some Python features that you may or may not have seen before. And we'll talk specifically about how that relates to our lab for this week. That on Monday, the concepts that we talked about with this functional programming and the map and the filter functions and the list comprehensions, those were specifically related to the homework assignment for this week. And so today is like talking about the lab for this week. So I'm going to start by sharing my screen. And then over here we have, or I have opened up, oops, I have the wrong week. I have last week's. Let's go to this week. I have this week's lecture notes opened up. And so specifically what we'll be talking about is memory management issues in Python. So things called local versus global variables, and then this thing about what copying in Python really means. That'll be like the majority of class for today. But before we do that, I just want to take a quick detour over to our issues tab and point out an excellent question that was just asked just an hour ago from our most recent assignment. And the question was about having an issue with the homework, and it followed the steps that I asked for really great of giving the appropriate amount of background information and all the information that I needed to provide the answer to Gate right here. There's a couple of formatting issues that I want to highlight though, so that you all are aware of them when you're creating your own GitHub issues, whether it's on this repository or any other repository on GitHub. And let's see, I'm going to go ahead and edit this comment right here. So as the owner of this repository, I can edit everybody's comments that you leave and put whatever words into your mouth that I want to put into your mouth. And I promise that I only do that for formatting sort of issues, but I could do it for whatever. And so here on this preview tab, the first thing that I want to highlight is that there's a quotation right here. An excellent thing to do, providing some context about why this is, why you're creating this issue. But for a quotation in Markdown, the specific Markdown command formatting syntax to use for that is this caret right here, the right arrow, the greater than sign. And now if we do that as preview, it gets this nice formatting. So it's really easy to see at a glance that this is a quotation right here. So if you're ever quoting, don't use quotation marks. Quotation marks are for English papers. In computer science world, we use these carets in the Markdown formatting to get nice display like this. The next thing is that there's a couple file names in here. So the readme.py, that's excellent, referring exactly to where which files are causing the issue. But anytime you're referencing a file in an issue, you want to put it inside of these single backticks like this. And this tells me anytime I see something in single backticks, it gives this nice formatting right here. And this tells me that this is something that's like exactly verbatim from a computer somehow. That either this was copy and pasted from a computer, or it's the name of a file, or somehow it's just, this is like computer code. So the name of a file, always put it in backticks. And this ensures things like if there's a space in the name of a file, or a weird character like a quotation mark or an underscore or something, that I know exactly where the beginning of, like exactly what is the contents of the name of the file. On Unix systems and or Linux in particular, and the Lambda server in particular, and this is different from Mac systems or Windows systems that you may have used before. But on the Lambda server and most computers in the world, file names are case sensitive. So actually this file right here, readme.py with some uppercase and some lowercase, this file doesn't exist. Instead, it should be readme in all caps like this. And that py extension is actually an nd extension, that this is a markdown file, not a Python file. So that's the right way to reference a file name. And then, let's see, there's one more file name reference right here. Let's change that to readme.md. And then the last thing is, anytime you have a command that you are talking about, we want, instead of using a single backtick, we want to use a triple backtick. So I'm going to put this on a line all by itself, and then triple backticks like this. And same here, we have another command right here, triple backticks. And these triple backticks should be on lines all by themselves. And now when I go over to the preview, you can see that rather than putting this piece of code in the middle of the paragraph, it separates it out into a big block. And that's important because it lets me know that this is actually like a full line of something, that at some point you hit enter. Anytime where you're copying and pasting something that somehow involves hitting enter, you should put it inside those triple backticks. So if it's a command you typed in on the terminal, or if it is a like multiple lines of Python code, put it in those triple backticks like that. And now this is a, not only is the content great of this question, but now the formatting is also perfect. So that is just a quick update on those GitHub issues. And again, I'm spending a lot of time stressing this because when you are contributing to other projects, this is one of the things that signals to the people that you're working with that you are a serious programmer who sort of deserves to have your questions answered and deserves to have somebody spend the time to solve your issues for them. Okay, so back to our week one here. And today we're essentially going to be kind of going step by step through the lab that you'll be doing this week. We're not going to do all of the lab, but we'll do some of the major parts of the lab. And the first of these is related to Git, and it's another pattern with using Git in GitHub. So previously, last week, we talked about how you create these pull requests when you have this upstream repo and you've made some changes to it and you want your changes to be included back in the upstream repo. This pattern that we have here is what to do when a downstream repo, so a downstream repo would either be your origin repository located on GitHub, or a local repository located on, say, the Lambda server or your laptop or any other computer. We call both of these repositories downstream repositories because sort of the upstream source, kind of with this analogy of this one being upstream, creates all the changes, and those changes flow downstream, flow down to these changes here. There's sort of three new commands that we have to do, and I'll open up a terminal here in a second to show you how to do them. But Git Pull takes information from the upstream repository, puts it onto your local repository, and then Git Push goes from the local back to your origin repository. There's no way in GitHub to go directly from the upstream to the origin. You have to involve a third computer somehow. So this 1 and 2 will be the sort of the main steps to take away from this pattern. But you also notice I have a lot of other numbers written out here. In particular, I have some negative numbers. So this, starting at -3, there's this fork happening, and then a clone at -2, and then this -1 of new commits happening in the upstream repository. I put those 3 steps as negatives because those are things that have sort of happened before you've started before we start this process. Those are the 3 steps that cause us to be in this situation of having to update our downstream repositories. So in particular, way back last week, or working on the first homework assignment in lab, you forked the class repository and you cloned it onto your local repository in the Lambda server. But then since then, I have made some new commits to the repository, and we need to update our origin right here with those new commits. So these negatives are things that have already happened. These positives are the things that you have to do. And then there's also a 0 step right here where that's a one-time setup thing. It doesn't matter when that is run, as long as this is run before you do the steps 1 and 2 right here. Okay, so that's an overview of like what this diagram is trying to show. I'm now going to switch over to the terminal and walk through the steps of how to do this. So here we go. Today I have only a single terminal window open, and I'm in the Lambda server right now. Currently in my home folder logged in as user test, and I'm going to go to my CS46 repository where I've already cloned it before. And here we go. Let's go into week 1. And this week, this repository, this local repository, is currently behind the Upstream repository. Because I've made changes to the Upstream repository that have not been included in the local repository. To see what those changes are, I have my example student Upstream repository, or sorry, my example student origin repository. This was forked from the Upstream repository right here. And you can see if I come down here, there's no information about what the lab is for this week. So our goal is to get all of this updated information about what the lab is for this week into this origin repository right here. In order to do that, the first thing that we have to do is that, well, actually, let me take a second and remind us in this chart. So steps -1, -2, and -3 have already been completed. Those are the background that sets up this scenario. So then the next step is step 0 here. We have to do this git remote add upstream URL. We have to tell our local Git repository about this upstream repository. Remember, when we cloned, we only cloned from the downstream origin repository. So by default, Git does not know about this one up here. The command to let Git know about it, git remote add upstream, and then the URL, github.com/mikeisbiggie/cmc-csci046, like this, and hit enter. And normally, if this is a successful, if you run this successfully, you're not going to get any output. Here, I guess I actually ran this command just before class, and so getting this remote upstream already exists. If you get this error message, that's okay. It just means that you've already run this command before, so you don't need to run it again. This setup command, this 0 command right here, again, you only have to run it once. You don't have to run it every time. The commands that we run every time are this 1 and this 2. Git pull upstream branch says to fetch all of the information, all of the new commits that are in upstream right here, and download them onto our local server. The upstream here refers to the sort of URL that we're downloading from, and branch here refers to the specific Git URL, or the specific Git branch that we want to download. In this case, the branch that we're working with is 2021 Spring, so my command will be git pull upstream 2021 Spring. Git pull upstream 2021 Spring. And you'll get output that looks like this. Kind of looks similar to when you did a git clone or a git push. And the main, let's say, you can feel free to ignore all of this output, but what it's saying, the main sort of meat of the contents is right here, where it tells you what are the actual files that are being updated with this git pull, and how many lines are there. Each one of these pluses represents a line that's added. Each one of these minuses represents a line that's deleted. So just by a quick glance, I can see that, oh, this did a lot of adding to my files. Whatever, I don't know exactly what it added. I just know it added a lot of stuff. So that's this step 1 right here, git pull upstream branch. And then my next step and my last step is this git push origin branch. Again, the branch is going to be 2021 Spring. So I'm going to press the up arrow to get back to this command right here. And I'm going to hold down the control key while I press the left arrow so that my cursor jumps. Notice that it's jumping over the whole words. So I only have to press it twice to get to the push and change those two L's to an SH. So it becomes from pull to push, hit enter. I have to type in my credentials now. Example student. Let's see, did I type in my password wrong?
Mike, aren't you supposed to push it to downstream and not upstream?
Oh, thank you, yes. Great, great point. If I come over here, notice that this number 2 right here says git push origin branch. I want to push to this repository right here. I was getting the error message that I don't have permissions because I was, instead of pushing to this repository, the one that's for my account, the one that I own, I was pushing to the upstream repository, which is one that is not my account, one that I don't own. So it doesn't matter what password I type in, whether it's correct or incorrect, I don't have permissions to do this, and that's why I was getting that error message.
And
so,
sorry, Mike, what you just said is in the perspective of example student, right? You're saying the origin repository is that of the example student, not Mike is Vicky.
Exactly, correct. So we'll change upstream here to origin. So git push origin, then the branch. And now type in my credentials. And looks like everything is working. No error messages, things got uploaded. And so back over here. So here is again the example students repository. And if I refresh this web page, come down here and we see that it has all of this updated content with the lab instructions. So the first step in your lab for this week is just to repeat this process yourself so that you're able to have access to all of the latest things that I upload to class.
Professor, I have a question. So,
yeah, go ahead.
So I think because you know, our last homework or our last lab, we didn't have like week 1 within our like downstream repository. So we would just repeat what you did, but not in the week 1 folder within the CSS or CSC 46 folder. Great
question. So here, back in the terminal, anytime you run a git command, it doesn't matter what the command is, whether it's git push, git pull, git branch, git checkout, any of these commands, it doesn't matter where in the file system you are, as long as you're inside of the Git repository somewhere. So here, I'm in this week 01 folder right now. And the question was, if you don't have a week 01 folder, what do you do? And the answer is, you don't have to be in the week 01 folder, but if you're anywhere in this CMC CSCI 046 repository, any subfolder of this folder, then all of those commands will work exactly the same way. The only thing that you have to make sure of is that you are somewhere within this folder. That if I cd ... one more time, you can see that I'm no longer in a Git folder and no longer in a Git repository at all. And the bash prompt tells us that because this purple section that tells us what branch we're in has disappeared. So no longer in a Git repository. And so if I were to run a command like this, git push origin spring, we'd get this error message saying not in a Git repository. Great question. Also, as an aside, you all have been doing a fantastic job of asking questions in this class, of interrupting me when you have questions and using the chat to ask questions. So I really appreciate that. Please keep it up. There's a good question in the chat right now about if I do a git push origin, does that overwrite the changes that I made to the continuous integration homework? And the answer is no. So the continuous integration homework is, I'm gonna come back over here and come back to, so right now I'm in the Upstream repository, and let's go back here to week 00. And this is a fantastic question that right here we see there's this homework folder that has the continuous integration homework inside of it. And so we might think that if you were to make some changes and update your repository, that it might overwrite any of the changes that you had made. And if this were a normal folder, if this right here were a normal folder that yeah, it was just normal, then that actually would happen, and your changes might get overwritten. You can see here, however, that this has this at and then a number off to the side, a hexadecimal number. This hexadecimal number is called the commit hash, and this folder right here is actually called a submodule in Git. So it's not a normal folder. It just looks like that through GitHub. And if I click on this submodule folder and pay careful attention to the URL up here right now I'm in the CSCI046 repository. But now if I click right here, it actually takes me to an entirely different repository. So now I'm in the continuous integration repository. And because your continuous integration homework was in a different repository, that guarantees that you'll never have a conflict where you try to update the stuff in the class and it will overwrite the things in your homework. Yeah, these Git submodules, it's okay if that's still like black magic confusing to you at this point. Just the takeaway message is that you're never going to accidentally overwrite your homework by doing one of these update steps. And another great thing about Git is actually every command that you type into Git is completely reversible. So if you do ever get into a situation where you think you've accidentally deleted your homework, or things are not working the way that you think they should be working, don't panic. I guarantee you that I can undo whatever you did and get you back into a sort of normal working state. Yeah, so great question so far. Are there any other questions about this new Git pattern? Okay, then from here we're going to move on to talking some more about Python. And we'll specifically be talking about these types of manipulating variables and some of the weird edge cases, very non-intuitive things that can happen in Python. And these are different than other programming languages as well. So if your first programming language or your first computer science course was in a different programming language, you'll want to pay extra attention here, because these will be very different probably than what you saw in your first class. So to illustrate some of these concepts in your lab, there is a PDF file, this lab.pdf, and that's what you'll be doing in the lab. And this PDF file, it's relatively long. There are 18 pages in this file, and each page has a small number of these sort of Python snippets inside of them. The instructions for what to do with these are all written right here, but I'll just go over it real quick verbally so that you kind of know what to expect. The idea is that each one of these Python, little miniature Python programs, you want to use Vim to type these programs in and then run on the command line and see what the output is. And some of them you will be able to predict what the output is before being run. Some of them you'll try to predict what it is, and you'll see that it's actually a totally different result than what you would expect. And these are that's sort of like what the main purpose of this assignment is to get you to see when Python does the things that you don't expect on these very small toy problems. And there's a lot of these small toy problems in here, but I've specifically taken them from past instances in this course where students have had some sort of major debugging problem that they've spent hours and hours racking their brains with, pulling out their hair's turned gray, and I've condensed that really frustrating problem down here just to its essence so that you can see that essence of the problem here, understand what the problem is before you get to that in a bigger homework assignment. And rather than wasting hours struggling with the computer later, if you really try to understand these problems now, it'll save you tons of time. For submission of this assignment, since it is 18 pages, I'm not asking you to scan all of these pages and upload them. I'll just take your word that you have completed all of these assignments, and on Sakai, you just type in, I've completed the lab, and you'll get full credit. So because of that, it might be tempting to kind of skim through this assignment and not spend a lot of time on it, but I strongly discourage you from doing that. That I guarantee 100% any time you spend on this assignment will pay off for itself tenfold throughout the rest of the course, because you'll be avoiding bugs that people who just kind of skimmed this assignment will encounter. Let's see, before going on to actually the content of the lab, are there any questions about the mechanics of it and what to do, what to submit? Okay, then we're going to start talking about the content. And I'm going to break my Vim rule just this once for this class. And we're going to use a website called pythontutor.com to visualize exactly what different snippets of Python code are going to do. And for this assignment, all those code snippets, you should at first type them into Vim to get more practice using Vim. Some of the assignments have specific instructions on like which key presses, which commands to use to get practice with Vim. But you should always feel free at any point in this class to use this pythontutor.com website to try to help you understand at a deeper level what's kind of going on under the hood in Python. So you're always allowed to use this website. And when you first go to pythontutor.com, you get this kind of big screen. It's not really clear what to click on, but you click on this button right here, start visualizing your code now. And that brings you up this little window where you can type in some Python code. And so I'm going to type in a very simple Python program right here, say xs equals 1, 2, 3, and then define example of ys equals 3, 4, 5, and print ys equals comma ys. Then down here we'll run our example function. And then after you type in your Python code right here, if you press visualize execution, then you come to this window right here. And on the left, in the top left, you can see the Python code that I typed in before is still there. And then on the right is going to be all of the, we'll see what these are in detail in a second, but all of the frames and all of the objects that are created as you run this code. This red line right here is the next line to execute in Python. Let me make this window a little bit bigger for everybody. This red line here is the next line that will be executed. And there's currently no green line, but if there were, that would be the previous instruction that's been executed. So at the very beginning, nothing's been executed. And then you can press next right here to walk through and run a single line. So from the very beginning, I press next, and it executed this xs equals 1, 2, 3 instruction. Here, what you can see is this created under frames, this box called the global frame. The global frame is where all of your global variables are stored. In Python, a global variable is a variable that you can access anywhere, whether you're inside of a function or not inside of a function. And the equal sign is how you define a variable. So this creates a new variable called xs. And then what this arrow says is that this variable xs refers, so the verb is this variable refers to this object right here. And this object is a list with the elements 1, 2, and 3. In Python, remember that all of our lists are 0 indexed, so it's 0, 1, and 2. Up here at the top, those are the indices, and down here, these are the values of the list. Now, when I press next again, we created this this variable right here, example, and this example variable points to the function object example. Notice that we did not execute this function, we just defined this function. We created it so that we can refer to it later. Now here on line 7, I press next, and it runs this example function. The red arrow now goes up to the top of example right here because we're now inside the example function. We're going to start executing this code here. Now this here is a second frame that got created. And in Python, a frame is any sort of collection of variables that you have access to. So we had this first global frame. Every Python program will have a global frame that contains the global variables that every function has access to. And then down here is what we'd call a local frame. And this frame is local to the example function. At this point, there's nothing inside of the frame because we haven't executed any code in the function yet. And I press next, go on to this YS line. Next, actually run that line. And we can see that it creates a new list object down here. And this one is a different list object than this one, which makes sense because it has different values inside of it. Press next again, and we can see that we just ran this print function. The output of that got placed up here in this text box. And the example frame, since it is a function frame, a frame that was created when we started a function, it now has this special variable inside of it called the return value. In this case, there is no return statement, so the return value is just none. But if I were to return a value, then whatever that value is would be placed right here. As soon as a function is done being called, its function frame is deleted and all of its contents are erased from your computer's memory. So now when I press next again, that example frame right here went away. You can still see that we have this example function that we can access to call this, to create a new example frame, but that example frame went away. Let's see, there was a lot of terminology and things going on in that first example. Are there any questions about that? There's a great question in the chat about when should you use local variables versus global variables. We'll get to that in a couple more examples, but that's a great question.
Mike, I have a question.
Mm-hmm.
So in previous defined examples, we there's a return X or return something. What's the difference between that and here the example?
So the question's about how there's no return statement here in this function?
Yeah.
Okay. Yeah, so let's go ahead and edit this code. And if we added return none at the end, then this Python function will do the exact same thing as it used to do. In Python, any function that does not have a return statement always ends with return none, sort of by default. Again, that's different than other programming languages. If you're coming from something other than Python, you probably were required to put a return statement inside of every function. But in Python, you're not required to. It just defaults to return none. If, however, we wanted to return an actual value here, we could say, for example, return ys right here. And now down here, let's say zs equals example, like this. And we'll see what happens. So visualize this execution and step through it a little bit until we get down to this return statement on line 6 right here. And so at this point, the code is exactly the same as it was before I made these changes. And again, the changes that I've made are I added this return ys line, and on line 8 down here, I am assigning the output of, or the return value of example to this ZS variable. And so here on return YS, now when I press next, you notice that this return value right here, it used to say none the very first time we ran this with the previous code, but now it has this reference. Again, this arrow is called a reference to this list right here. Some people will call these arrows pointers because in other programming languages, they're called pointers. But technically a reference and a pointer are something slightly different. So in Python, it's most correct to call these arrows references. And now what you have here is you see this YS variable references this list object here, and the return value also references this same list object right down here. If I press next one more time, now you'll see that this ZS variable was created in this global frame up here. And this ZS now references this list right here. The reason for that is because it was the return value of the example function. So whatever the return value is, whatever it references, is going to get what the ZS references. And that's because ZS is to the left of the equal sign here. One of the potentially confusing things in Python is what's the difference between a print statement and a return statement. And this is hopefully starting to illustrate that the print statement, the things will come up here anytime you say print, but there's no way to access any of the information that's been printed. So just because I had print right here, I can't actually assign that to a variable. If I edit this code again and take away this return statement right here, so I'm still printing, but now there's no return. And remember, the fact that there's no return is equivalent to having return none. So I'll just put this in a comment like this to remind us that it's equivalent to having return none. Now I press visualize execution, walk through, get back to this same location, but now the return value is none. So this ZS variable will now contain the value none right here after this whole code is executed. These are all great questions so far. Any other questions about this or anything else we've talked about? Okay, so next I want to talk about one of the sort of mechanics of these variables inside of functions and local scope. So here I called this variable YS to be very explicit that this is a different variable than the variable XS. But what would happen if instead I called this variable XS like this? So now both of these two lines right here, the left-hand side of the equals is the same value, but the right-hand side of the equals is different values. And let's see what happens. Let's change this down here so that it's printing out the XS values. We'll visualize the execution. And now go next, go inside of the function. Up to this point, everything is the same as it used to be because all the code that we've executed is still the same. But now when I do this line 4 right here, it's going to add this new XS variable to the local frame of example. So here now we have two XS variables that have been defined and that we have access to. Once you put a variable in the local frame, however, that has the same name as a variable in a global frame, it's not technically impossible to reference this variable anymore, but it's essentially impossible. You can no longer easily reference this variable. And so this XS, in some sense, overwrites this previous XS right here, because when I do this print statement now on line 5, it's going to only know about this XS, and it's not going to have access to this XS right here. So this is one of the first very confusing things about Python, and this is a very common source of bugs, is that students will create local variables that have the same names as their global variables and get confused about which one of these two variables are you referring to. It's a good development practice to never have this situation even come up, to always name your local variables something different than your global variables. But in practice, you can't guarantee that's always going to be the case. And there are situations where you just can't have that. So you do have to be aware of how Python works in these scenarios, that these local variables take precedence over these global variables. A local variable is defined only when you actually have something like this equals and put something to the left of the equals like this. That's the only time that something actually defines and creates a new local variable in this local function scope. Let's go back and edit this code. And instead of saying xs equals 1, 2, 3, I want to do, so I'm going to go ahead and comment this out. I'm going to say xs dot append 3, xs dot append 4, and xs dot append 5, like this. So now this is calling a function. So this dot append is a function, and this function modifies the xs variable right here. And in particular, it adds these values 3, 4, and 5 to the end of the xs list. It's very tempting to think that this might create a local variable because we're kind of doing something to this xs, but you only create a local variable when your variable is to the left of an equals sign. So if we visualize this execution and walk through it, so now line 5 here is the first line inside the function. I press next, and you can see that it actually did not create a local variable down here under example, and instead modified this one up here, this xs. 1, 2, 3, and there's the 3 from line 5, then a 4 from line 6, and a 5 from line 7. Printing it out, we get all of that. There was a great question a little bit ago about like when should you use a local variable versus a global variable, and this is sort of a kind of a stylistic question about that other people will, reasonable people disagree on this answer about when to use a local variable versus a global variable. But the general principle is use a local variable whenever it's possible, and only use global variables when you must. So the reason everybody agrees that this is the right principle that you should follow, some people disagree about like possible. Some people are really willing to stretch the boundaries of possibility to use local variables. Some people are a little bit more flexible on using global variables, but this is the general principle that you want to follow. And so as an example, let's say we had a for loop inside of this function, something like for x in xs, print x equals x, like this. Here, this is going to be a local variable. It's a variable that only exists inside of this function. And it kind of makes sense that since this variable is really like kind of part of this for loop, that it there's no need for it to be a global variable. And it's very easy, very possible to make it a local variable. So for loops, looping variables, that's sort of the most common, easiest situation to think of when you're wanting to have a difference between local and global variables. This variable up here, the way this function is written currently, it could be a local variable and everything would still work. And I just made it a global to kind of illustrate things. Let's say we had another function of example 2, and then in this function, it would be also referencing this xs variable. Now, because both of these two functions are needing to reference this XS variable, this would be a situation where you would have to use global variables and you cannot use local variables. This comes up very commonly when you have configuration settings. So like maybe you have a username variable, and so make that be my username, and then many different functions need to reference what your username is. And we'll, yeah, again, throughout the course, see lots of examples similar to that. Any questions about local versus global variables so far?
Do global variables take up more memory, or like why is that the convention?
Great question. So in terms of like memory usage or performance, those kinds of considerations, there's actually no difference between a global and a local variable. The reason why this is sort of the principle of making variables local whenever you can, and people really like try to make as much stuff local as you can, is because it makes debugging things a lot simpler. That having everything that this function needs just contained right here in this one space makes it easier to sort of follow and understand what this function is doing. And it also guarantees that no code nowhere else in your program can modify what that variable is. So here, maybe my example function is somehow implicitly assuming that this variable is set to some value, but before I call that function, I redefine it to be something else. And this could break your this function from working properly without you really knowing why. So it's a little bit of an abstract explanation, but that's kind of the general principle. That just makes debugging simpler. Great question. Any other questions so far? Okay. So this is maybe all seeming like reasonable, something that you might have guessed how Python worked if you kind of sat down and thought about it. So now let's start thinking about things that are in like the weird kind of situation, things that you probably wouldn't have guessed. And the first thing is that you can actually define functions inside of functions in Python. So here I have this example function. I can define an internal function like this. And this internal function will make it take a parameter x, and it will return x plus 1. So it'll just add 1 to whatever its input is. And then down here, we'll, instead of printing x, we'll print internal of x like this. And I'm going to delete all of this, and I'm going to delete this as well. So now, yeah, so this is probably new, seeing functions defined inside of functions. That's perfectly okay in Python, very common actually. You will see this in real code. And now we have an x right here, which is used as a, for our for loops. And we also have this separate x right here, which is the parameter to this internal function. And this will help explain maybe why we care about these frames and these variables and keeping track of them. So here, let's get inside of our example function. So everything over here on the right-hand side now is the same as it used to be. But now the very first line, line 4 right here, is going to create this new function internal. Internal is the definition for a function. So it defines the function right here, but it does not call the function. And so because it does not call the function, we do not get a new function frame. We do not get a new local frame. Now we have this for loop right here. That for loop creates this new variable x internal to the frame for the example function. And now we have this really complicated function right here, print, and then, or this complicated line here. And this line is complicated because it has two function calls inside of it. It has this print function and this internal function. when I press next, you can see that we're going inside of the internal function. We always evaluate in Python from the inside out. So because internal here is inside of the call to the print function, we evaluate internal first. And this creates a new function frame for the internal function. This function has a parameter x, so that x is placed instantly on the function frame right here. And this x, again, is different than this x right here. They refer to two different things. Here, now the return, x plus 1, so it's referring to this one right here. 1 plus 1 is 2, that's our return value. So this internal x will get replaced by 2, and that'll get printed up here. Redo that, and you see that it keeps every iteration of the for loop creating a new internal frame for that function call. And then down there at the end. Are there any questions about that? This is a great question in the chat right now. We have this internal function inside of example, and the question is, can I call this internal function outside of the example function? And the answer is no. The reason why, looking at this over here, you know that the answer should be no, is because when you're outside of the example function, let's say we were to add a line 12 after this line 11, so we're outside of the example function. That means that the only frame that you have access to is the global frame. If you're not inside of a function, you only have access to the global frame. If you're inside of a function, that's when you have access to the frame that is for that function. So if I'm outside of this example function, I do not have access to this internal variable right here. And this internal variable is the only variable that's currently referencing this internal function object right here. So I can't access this internal function unless I'm inside of this example frame. Yeah, so there's a great question in the chat about what makes internal functions advantageous in production environments. And the answer is, again, related to debugging situations that because this internal function cannot be accessed outside of this example function, it just makes it really obvious that the code here belongs to example. Yeah, this is still a very abstract discussion. As we see more sort of concrete concepts throughout the course, we'll be revisiting all of these concepts, kind of answering these why questions. Why would you ever do this versus do that later in this course? At this point, the thing to focus is just on the mechanics of what is internally going on in Python when you see these constructions. Yeah, until you have that kind of intuition about the what, it's very hard to talk about the why, because the why really requires, say, a 100-line Python program that does something fancy.
Mike, really quickly, can you go back and go through the internal function steps again, just so I could see
Sure.
kind of what's in that frame?
Sure. So here, again, just like on a globally defined function, when you're on a locally defined function, when you hit the DEF part, that only defines the variable and creates the object out here. It doesn't actually run the function. And you only run the function when you actually call it. So when you get that internal with the parentheses right here, press next, comes in here, and now here is the frame for the internal function. And press next, and we get that return value right here. So that's the sort of final state of the frame.
Okay, awesome. Thank you.
Mike, so what if you put 4x in excess before the second define term?
So if we moved lines 7 and 8 up above line 4?
No, you move line 7 above line 4.
Ah, okay, yes. So let's go ahead and edit this code and do this, move that up here, and something like this. So this is still valid Python code, and this is a little bit unusual, not something that you would see very often of a function defined inside of a for loop, but it's something totally allowed to do. And what's going to happen is that every time we hit this line 5, it's going to redefine a new function object over here. It's also going to delete the old one, so it's a little bit hard to follow along with Python tutor exactly what's going on. The actual output up here is going to end up being exactly the same thing. Yeah, I'm not sure if that's a fully satisfying answer, but that's the answer. These are all great questions. Are there any other questions so far? Okay, so let's edit this code again and move this back up here. And we're going to do something a little bit crazy now. And that's that we're going to recall about this whole idea of functional programming, that when you refer to a function, you don't actually have to call that function. And so yep, that looks good. And instead of saying ZS equals example parentheses, I'm going to say ZS equals example. And then down here, ZS parentheses like this, and visualize this function. And let's step through. Let's see. Sorry, I went a little bit too far. Let's go first back to the beginning. Next, so we're going to define that function. Now in line 11 right here, when we have ZS equals example, notice that when I press next, it does not execute this example function. Instead, it creates this new variable down here, which also references this function object right here. So now both example and ZS reference the same thing on the right-hand side over here. They reference the same object. So when I do ZS parentheses, the parentheses is what actually calls the function object, and it's going to call it exactly the same as if I had done example parentheses, because they're both referencing the same thing over here. Press next, and it goes into this code and does everything exactly the same as it did before. Once you're inside of the function, there's no way for you to know whether it was called actually as example or whether it was from some different name. So one of the principles of functional programming in Python is that once you're inside of a function, you can't know anything about the outside of the function and how that function was called, unless it was passed in as a variable. So this is maybe not, I don't know, maybe it's surprising, maybe it's not surprising. It's definitely a little bit weird. But here's something that we're going to get into the really weird things. So now we'll call it foo down here. So here I have my example function, and now I'm returning internal right here. And so notice again that I'm just returning the function, not the call to the function. So right here I'm calling the function. Right here I'm not calling the function. I'm just referencing the function. I'm returning the reference to the function. And let's see, foo of 3, say, what was that? Print bar equals comma bar, like that, and visualize the execution, what's going on here. So run through this up until we get to that return statement. Everything's exactly the same as it was last time. And now we're currently on this return statement right here. So this is where things are going to get different. I'm going to press the next button, and notice that it did not create a new frame. It did not create an internal frame like it did when I called the function here. Instead, it's put a reference in the return value to this function object over here. So now internal inside of the frame references this, but so does the return value. It also references this. Now I'll press next, and here's where sort of the magic just happened. I now have a foo over here from this line, foo equals ZS. Foo points to this object which was created inside of the example function over here. So this function object is in some sense local to this function, but it's also, we'd say it's escaped its scope. It's now accessible not just from the local scope, which doesn't exist anymore. This frame has been deleted. It's just grayed out so that you know where the original origins of this object were from. And now this function has escaped its scope and is accessible from the global scope. So bar equals foo of 3, run that. It creates this internal function, or this internal frame again right here. Because we have parentheses, that means it's a function execution, and it will run that function, add 1, and return, and then print out bar equals 4 up here. So it is possible for functions and variables to escape a local scope and become global, but that's a sort of, it's actually a very common thing that we will encounter, but it's also a weird thing. It's not not something that should feel obvious and intuitive. Are there any questions about that? Okay. Yeah, if you are feeling like there's a lot of stuff going on right now, that's totally okay, and probably where you should be at. If you're feeling like all of this has been 100% obvious so far, and why are we even going over it, then my guess is probably you are maybe missing some of the subtleties about what's going on here. That this really is like weird things going on here, and mind-bending, hard to wrap your brain around. We're going to switch tacks now. So this is all about the scope management, the local versus global variables. And now we're going to move on to what in Python is called the assignment versus the copy versus the deep copy problem. And so let's delete all of this and create a new variable yx, assign it to be equal to xs, and then I'm going to say ys of dot append test like this, and then print ys equals ys, and run this. And so the very first line creates our variable xs referencing this list over here. And now when we do this assignment operation, ys equals xs, you notice that this ys references the same object over here on the right. And so when I do ys.append test, we've added this string test to the end of the list. Again, in Python, lists, we sometimes say they're heterogeneous. They can have as many different types in them as you want. They can have lists, they can have strings, they can have other lists, and there's nothing enforcing that it's the same type inside of here for each element. But the important thing about this line 4 and 2, how they work together, is that because ys references the same list that xs references, when I modify ys, I also modify xs. So here I'm printing out ys equals ys. We get that up here. See, I meant to actually print out the xs variable, so let's just print out both. Like this. Visualize that execution and run it all the way through. And you'll notice that both of these two variables get the same exact thing printed out. So when I modified ys right here on line 4, because ys and xs reference the same list over here, when I modify ys, I also modify xs. And this is a very, very common cause of bugs in code, is sometimes you want this behavior where two variables reference the same object, but usually that's not what you were intending. Usually you probably wanted ys to be a new list object that was a copy of xs. In Python, in order to make a copy, you have to import a module called copy. And then here on this line right here, instead of saying ys equals xs, you say yx equals copy.copy xs. So this is a little bit redundant looking, because you have copy and copy twice. This copy is the name of the module, and then this copy right here is the name of the function inside of the module. One of the things I personally don't like about Python is that it's very common for to have modules that have functions inside of them with the same exact name of the module, and so you see things like this pretty frequently. With this copy module, it's very common to, we call this a fully qualified import, and this is a fully qualified call to the function copy. Qualified mean I'm telling you exactly where the function came from. It came from the module copy. But because this is redundant, sometimes instead of doing this, you'll see people do, so comment out that line, comment out that line. You'll see from copy, import copy. So you get the redundancy up here. And then down here, you can just say ys equals copy of XS. Both are good Pythonic style. Some people prefer this. Some people prefer this. I personally like this option the best because it makes it clear exactly where this copy function was defined from, and it's not something that I wrote in my own code. So, so that's what I use. Let's visualize this and let's walk through. And now the key difference, I guess maybe let me back up to the beginning. The first difference that you'll notice is that this copy variable has been introduced and it refers to a module. So that's all this says, is that we have this copy now that refers to a module somewhere. The key difference though is going to be on line 5 when I execute line 5 right here. Now when I press next, you'll see that ys does not refer to the same list as the XS list. Instead, it refers to a brand new list that's just been created. And now when I append to the when I append to ys, it no longer modifies XS. And so these two things get different results up here. Are there any questions about that? That's a key concept, key observation is that if you want two different objects over here, you have to use the copy.copy. Okay, so that's the basics of this copy problem. Now let's see some more advanced versions. Let's instead of having just one list like this, I'm going to have XS be a set of nested lists. So lists of lists. So the first list will be 1, 2, 3, and the second list will be 4, 5, 6, like this. And we'll first see what that looks like in here. So now our XS list, our XS variable right here, it references this list right here, but this list is not just a normal ordinary list. Instead of having numbers inside of it, it has references to other lists inside of it. So this list right here references 1, 2, 3, and the second position references 4, 5, 6. When I go down to the copy function, you'll notice that ys now has a new list that it's referencing here, but that list references the same internal lists. So it references both have the same 0 position here and the same 1 position here. When I append to ys, that doesn't change anything. It still only affects the ys list and does not affect the XS list. But if I try to modify one of these lists, it will affect things. So let's go back and edit this code. And now I'm going to do ys at 0. So ys at 0 is going to reference this list right here. And I'm going to say, do that dot append test, like so, and visualize the execution. Run through here. So XS created these same kind of trees of lists. And now at ys, I created this one right here. So 2 different lists, but the items inside that list reference the same objects. When I append onto the list itself, that works as you would probably expect, as we saw before, adding only to the ys list. But now when I append to ys at position 0, Well, ys at position 0 references the same list as xs at position 0. So when I append to it, it has to modify both ys and xs. I print those out, and we see that at position 0 here, it has a different list, or sorry, it has the same values. It has the same values because they are both referencing the same object over here. This sort of nested references is really where this copy assignment problem gets really confusing, and keeping track of when is a reference referencing the same thing versus something different. If your goal was to actually copy everything about the XS object, including its entries down here, then it's not the copy.copy that you want, it's copy.deepcopy. That. Visualize that execution, run through. Now when I do copy.deepcopy, you can see that not only did it copy the actual list object itself, it also copied the places that it pointed to. So copy copies only the immediately referenced object and leaves all the other references pointing to the same objects. Deep copy copies both the immediately referenced objects and everything referenced underneath. And now when I append here, it only appends to the ys, does not append to xs. And when I append to the 0 entry in ys, it only appends to the one inside of ys, does not affect the one inside of xs. And so now when I run those, I get this up here, where xs totally unchanged, ys changed in multiple locations.
Professor, I have a question.
Go ahead.
What would the command be for like a 3-dimensional list?
Great question. So deep copy goes totally nested no matter how many like nestings that you have. So we can make this, I'll make it 4-dimensional like this. There we go. There we go. Matched all the parentheses. So it's 4-dimensional here. Now I'll do xs at 0, at 0, at 0. So it's going inside 3 locations to do this. Visualize that execution. And I'll just hit the last button so that we go all the way through. And you can see that the things are very complicated here because there's so many levels of indirection, but everything is completely separate between the XS and the YS list. And if we came up here to the top, we'd see that this test string doesn't appear anywhere in XS. So deep copy does everything. Copy does just one level, and there's no sort of default built-in way to do only 2 levels or only 3 levels. I can't imagine a situation where you would need that, but if you did need that, you'd have to implement it yourself. It's a great question. We're pretty much out of time for class today. So we've covered everything that you need for the lab at this point. The actual lab assignment is going to combine all of those things that we've talked about in even more interesting and convoluted ways, but again, in ways that actually have come up in students' homework assignments. So really good one to pay careful attention to. It will definitely pay off throughout this course. And it's also a really good time to get more practice with Vim. I know for most of you, Vim is probably still like a, like, why should I even care about this? My hands are so slow at all these weird commands. I don't know what they are. This is the time to practice that. So in the future assignments, when things get even more complicated, Vim is starting to be simpler and you can focus on the actual code. If you do have more questions, I will be sticking around for office hours right now, but that is our end of class. So I will see you all in lab tomorrow or class next week.